Okay, pencils down. End of test. So for this afternoon's keynote, we're very lucky to have Naga Govindaraju from Microsoft here to speak to us. And he's got a great job, I think, at least from my point of view, in the incubation group, which sits between research and product. So he actually gets to do research, but he also has a prayer of the things that he's doing, making their way into product and real technology. Naga was at University of North Carolina before that, and I think finished his PhD in record time. I'm going to embarrass him a little bit here. And he was doing GPGPU back in the old days when it was called GPGPU, and you had to do it through the graphics APIs, and you had to suffer. So now life is easy. So he's going to tell you about some of the things he's been doing recently. So welcome, Naga.
Thank you, David, for the introduction. So today I'm going to talk about Sort Benchmark, and this is a database benchmark. It's been there for over 25 years now, and I'm going to talk about its relevance for many core computing. Benchmarks are kind of interesting to us mainly because they drive the industry, and they also help the consumers realize the potential of the hardware and the software. So the question is, why is sorting an interesting benchmark? So to motivate this, I'm going to quote two famous computer scientists who have contributed significantly to the problem of sorting. Don Knuth from Stanford University said that, I believe virtually every important aspect of programming arises somewhere in the context of sorting or searching. In fact, Don felt so compelled by the problem of sorting that he has written an entire book devoting several hundreds of pages on the problem of sorting in his classic work, Computer Programming. So if I rephrase the quote from Don, sorting is such a fundamental primitive that arises everywhere in programming that it is important for us to get it right. The second quote that I'm going to talk about is from my friend Jim Gray at Microsoft Research, and he recently said that there's a lot of effort on multi-core processors and comparatively little effort on addressing the core problems, the memory architecture and the way processors access the memory. Sort demonstrates those problems very clearly. So if I rephrase my friend Jim, sort is an important kernel that illustrates how the design of the underlying memory architecture is, and also the way processors access the memory. So it serves as a good benchmark for even the hardware vendors. In fact, there is a whole bunch of community which worked on the problem of sorting, and these include researchers from high-performance computing, database systems, computer graphics systems, programming languages, etc. Sorting is also used as an intermediate step in the popular Google MapReduce algorithm, and last but not the least, it is also used as one of the benchmarks to measure the performance of the current CPUs. One of the areas where sorting is quite widely used is in the organization of massive databases. Today, terabyte datasets are quite common. Just to give some perspective, Google sorts more than 100 billion index terms, and there are over 1 trillion records in the web that need to be indexed. So adding to the complexity, the database sizes are rapidly increasing. In a recent survey from wintercloud.com, the maximum database sizes today are increasing at a rate of nearly 3x per year. And this is significantly more than the processor improvements that are being provided by the hardware vendors. So the processor improvements are not matching the information explosion. Architecturally, the problem of sorting could be done on two main commodity processors today, a CPU with a modest amount of high-speed data caches, and a GPU with a large amount of video memory and has high bandwidth. And the GPUs in the CPU could be connected by a PCI Express bus, as shown over here, or in more sophisticated architectures, there could be system-on-a-chip configurations. So it is important for us to understand how the performance of sorting is on these two kinds of architectures. So in the rest of the talk, I will first describe some of the issues in implementing sorting on the CPUs, and then talk about some of the issues on implementing sorting on GPUs. So massive data handling on CPUs often require random memory access. This is mainly because the data doesn't fit inside the small CPU caches. In recent research from database community, we have observed that random memory accesses are significantly slower than even sequential disk accesses. So the problem actually shifts from the I/O to actually memory performance on PCs. Adding to this problem, the memory to compute gap has been widening over the past several years. Architecturally, the CPUs are quite deeply pipelined, and they do not have a sophisticated memory architecture to hide the latency well. Therefore, whenever there is a cache miss, there is a high penalty, and the application incurs a high CPI. So due to these reasons, the CPU is often underutilized for many of the data-intensive applications. So how is the performance of sorting on CPUs? So Jim Gray at Microsoft Research used to maintain this benchmark called Sort Benchmark, and this benchmark maintains the world's fastest sorting records. And over here, I'm showing a log-scale plot of the number of records that are sorted per second per CPU. And you can notice that the performance of sorting over the past decade on the CPUs has not improved significantly. And this is actually an issue. Later on, I will talk about a new algorithm that we have done in 2006, which is performed on the GPUs, and talk about how we can design a potentially scalable solution on GPUs. So the graph illustrates that sorting is still a hard problem today, and I will describe, as I mentioned earlier, the GPU is a potentially scalable solution to terabyte sorting and scientific computing. So graphics processing units are nothing but commodity processors for graphics applications. They are mainly designed for graphics applications. Today they are becoming even more general purpose that they can handle a large variety of problems. GPUs are today available in almost all computing devices, including cell phones, laptops, consoles, desktop PCs, and even PSP devices. Their ubiquitous nature, coupled with the massive scales of economy, make them a very cheap and attractive computing device. GPUs are also massively data parallel processors. They have nearly 10x more operations per second than CPUs. So this chart over here highlights the amount of parallelism which is available inside a recent high-end NVIDIA GPU. And you can notice that the peak flops on a GPU are nearly 10x more than the CPU. So if your application is data parallel and it is compute intensive, you will see significantly higher performance improvements on the GPU than on the CPU. GPUs also have a high memory bandwidth, which are good at hiding the memory latency. They are becoming more and more programmable, and they have nearly 10x more memory bandwidth than CPUs. So this is how a traditional GPU pipeline used to look. I mean, there used to be a bunch of graphic stages over here. The programmer maps the algorithms to these graphic stages, and the data is written into the video memory. Architecturally, there is a high amount of parallelism within each of these different stages, and due to the massive amount of parallelism, they are able to hide the memory latency better than the traditional CPU architectures. GPUs also have a high amount of memory bandwidth. On today's high-end GPUs, you can get nearly 140 gigabytes per second access to the memory interface. As I mentioned earlier, GPUs are becoming increasingly programmable. In DirectX 11, we have the notion of a compute shader, which is designed to make GPUs more interoperable with the general-purpose computing. So a game programmer, can design his algorithms on the graphics pipeline, write the data structures through the traditional pipeline, and a GPU programmer can access these data structures using the compute shader APIs without worrying about the graphics pipeline, and be able to utilize the same amount of efficiency as you can obtain through the traditional graphics pipeline. GPUs have a high growth rate. You might have seen a number of graphs about the computational performance improvement on GPUs. This graph over here shows the memory performance improvement on GPUs over the past 6 years. And you can see that in February 2002, the performance has been nearly 10 gigabytes per second, but this memory performance has consistently increased over the past 6 years. And today we get close to 140 gigabytes per second. So many applications are indeed memory bound, and GPU architects got it right in terms of improving the memory performance and having a balance between the compute and the memory. So if your algorithm is memory intensive, you can see significant performance improvements if it maps well onto the GPUs. Now let's look at some of the issues on performing sorting on GPUs. Firstly, randomized writes on GPUs are still expensive. Therefore, optimized CPU algorithms may not map well onto the GPUs. There is a lack of support for recursion, and there is a paper in Graphics Hardware which talks about the issues of implementing quicksort on GPUs. Also, GPUs have a limited amount of memory. Therefore, if your datasets are quite large, you need to design out-of-core algorithms. So here's an outline for the rest of my talk. I'm going to provide an overview of the sorting algorithms, and then talk about how we have implemented sorting on GPUs, and then allude to some conclusions and future directions on where GPUs are heading. So at a broad level, sorting algorithms can be classified into 3 categories: adaptive sorting algorithms, which work well on almost sorted databases; general sorting algorithms, which work well on randomized data; and external memory sorting algorithms, which work well on datasets which do not fit inside this main memory of the PCs. So as I mentioned earlier, adaptive sorting algorithms take into account the extent of sorted nature inside the data, and these kind of datasets are quite common. Now, prior adaptive sorting algorithms require randomized writes. Moreover, in algorithms such as insertion sort, a processor may need to operate on different number of elements, causing load imbalance issues. Now, in this talk, I'm going to talk about a data parallel algorithm being implemented on GPUs using some of the common data parallel primitives such as scans. Our goal over here is also to avoid the load balance issues by distributing the workload efficiently across the processors. So, we're going to talk about an algorithm that we published in i3 2005. The algorithm was mainly designed for visibility ordering, which is nothing but a topological sort. But the same principles apply if you are sorting a linear array. So at a high level, the algorithm proceeds in multiple iterations, and within each iteration, we use a 2-pass algorithm. The first pass computes an increasing sequence, M, and the second pass computes the sorted elements in M. And then we iterate on the remaining unsorted elements. So what do I mean by an increasing sequence? Given a sequence S with n elements, an element xi belongs to the increasing sequence if and only if xi is less than or equal to xj for all elements xj in S. So you don't need to go over the definition. I will show a graphical illustration of what this means. Given n elements x1 to xn, an element xi belongs to the increasing sequence if it is less than or equal to all elements to the right of it. It's very simple. And if you consider all such elements, it is trivial to see that it is an increasing sequence. So how do we compute an increasing sequence? To do this, we scan the elements in the order n to 1. And at each element, we compare it against the current minimum. So at the beginning, there is no minimum, so we start with infinity. At an intermediate element, xi, we compare it against the current minimum. Now, if the element is less than the current minimum, we prepend xi to the increasing sequence, and we update the minimum. We do this for the remaining elements. Note that this is all serial at this point of time, and later I'm going to talk about how this will be made data parallel. Now, given this increasing sequence, how do we compute the sorted elements? So for doing that, we use the following theorem. Again, I will show a graphical illustration of what this theorem means. Given the increasing sequence M and the rank of an element xi in M is determined if xi is less than minimum of elements which are in I but not in M. So let me show a graphical illustration of what this means. So given an element x1 to xn, the elements in the color red, let's say, are in the increasing sequence. Then for any element xi over here, we know that by definition it is less than or equal to all the elements to the right of it. We also know by the definition of the increasing sequence that xi is greater than or equal to all the elements in the increasing sequence and to the left of it. So we know the rank of the element xi if it is less than or equal to all the elements which are not in the increasing sequence, but in I. And in fact, the rank of xi will be the rank of the element inside the increasing sequence. So how do we compute the sorted elements? Again, it's a linear time algorithm, and we maintain the minimum. So again, we scan the elements in the order 1 to n, and at each element xi, we first test if xi is in the increasing sequence or not. If it is not in the increasing sequence, we simply have to update the minimum. If it is in the increasing sequence, we compare it against the minimum. And if it is less than or equal to the minimum, then you need to append xi to the sorted list. And we do this for the remaining elements. So how long does this algorithm take to terminate? So in order to answer that, we use the notion of Knuth's measure of disorder. Given a sequence I and its longest increasing sequence, the sequence of disordered elements y is given by I minus its longest increasing sequence. And we use the following theorem to prove that the algorithm terminates into y plus 1 iterations. So what this means is that if you have a sequence which is almost sorted, then you need only a few iterations to sort the entire sequence. And this is not like the deterministic algorithms such as Pythonic sort, which require the same number of steps to perform the sorting on the sequence. So I'm not going to give a proof of this, but I'm going to show a pictorial illustration of what this means. So if you have an element, and let's say the elements xl plus 1, xm plus 1, and xq plus 1 are disordered, we take 2 iterations to sort all the elements which are less than or equal to the smallest disordered element. So, and then we take another 2 iterations to sort another disordered element, and all the elements less than or equal to it, and so on. So in 2 iterations, you would be able to remove all the disordered elements, and then 1 more iteration at most to sort the sequence. So here's an example of how the algorithm works. Here we have 9 elements, and we have one disordered element, which is 8. And in the first stage, we compute the increasing sequence. So all the elements except 8 are less than or equal to the current minimum. So only the element 8 is not in the increasing sequence. And in the second stage, we compute the sorted elements, and again, all the elements which are less than or equal to 8 are sorted. So in one step, we have sorted all the elements except 8 and 9. I distributed to see that in another iteration, 8 and 9 get sorted. So in 2 iterations, we'll be able to sort the entire sequence. So in order to compute the increasing sequence and the sorted elements efficiently, we use the notion of scans. So the definition of scan is given below. Given an input sequence a1 to an minus 1 and a binary operator plus and an identity element, the scan is nothing but application of this operator on each element preceding to it. So it could be considered as reductions of all the elements before it. So how do we compute an increasing sequence? We just need to do a min scan of all the elements in the backward direction. Let's say the min scan is nothing but a sequence I prime. Then all we need to do is compare each element in the input sequence with the corresponding element inside I prime. And elements which are less than the corresponding elements in I prime are in the increasing sequence. Similarly, in order to compute the sorted elements, we just need to compute the forward min scan of elements in I minus n. and let us say the sequence of things is I double prime. So in order to do that efficiently, all we need to do is take the elements in M, and which are not in, so for all elements which are in M, which are not in the including sequence, you just set it to infinity and perform a scan on I. After we compute the forward min scan, we just need to compare the elements in M with I. And the elements that are less than or equal to the corresponding elements in I are sorted. So data parallel scans are very well studied in the literature of parallel computing. They have been implemented on GPUs using the traditional GPU APIs by Horn in 2005. There is more recent work from Harris et al. In 2007, same book by Rao in 2007. And they all exploit the shared memory to achieve higher memory efficiency. There are also several optimized libraries which are available from NVIDIA called CUDA-PP. And in a recent paper that we published at ACM ICS 2008, we showed that the traditional tree-based scan algorithms may not actually scale well with shared memory. So instead, we presented an algorithm which uses matrix-based representations and show that it can scale actually better than tree-based scan algorithms. For people who are interested, the paper is available in ICS 2008. But here's a simple graph which shows the performance of the scan algorithms that we have implemented on the GPUs using the CUDA programming API. And here we are showing the relative elapsed time compared with some of the optimized libraries available from NVIDIA. And we can notice that our algorithms in some cases are nearly 2x faster, and in other cases it's like 20 to 40% faster than the current state-of-the-art libraries. So some of the lessons that we have learned when we have done the adaptive sorting is we have not gone and tried to remap the serial adaptive algorithms such as insertion sort onto the GPUs, and these may not be the right strategy for getting good performance. Another thing that we kept in mind is to design data parallel algorithms that achieve scalable performance. So we have not implemented the tree-based scan algorithms which may not scale well in the longer run. And I've shown an algorithm which is actually linearly input size and sorted exchange, and it works well on almost sorted input data. So this is one kind of an algorithm which works well on data parallel architectures. The last one is to use the data parallel primitives which can be quite optimized such as scans and use them to implement your algorithms. Any questions so far? So, let me go back. Talking about this one. This actually, most of the algorithms over here are limited by the main memory performance, so it's memory limited. It's often thought that yes, they're all memory bound.
And are these tests all based on that implementation, or based on other kinds of
What?
based on the new adaptive implementation?
The adaptive sort, so this, I'll come back to this later on. This has to be done on large databases which do not fit inside the main memory. So far I'm just talking about inputs which fit inside the main memory. I'll later talk about how we have actually broken the record by using the GPU data sort. Get back. Any more questions? Yes. So for the adaptive sorting algorithm, actually we have tried to solve a more complex problem called topological sort. So the topological sort is nothing but a depthless traversal of a tree, and it's something which comes in graphics if you know put the problem for order infinite transparency. So if you have an environment and you want to basically say render a building in glass, you want to have a transparency effect. So you need to traverse the triangles in order, starting from front to back. So if you need to have that, there are all kinds of dependencies over there. So that's the problem that we wanted to actually solve. And for doing that, we actually used a feature available on the NVIDIA GPUs called the occlusion query at that point of time. And that was mainly, so to answer your question, basically we wanted to have a data parallel algorithm. And at that point of time, the only mechanism that we had was to use an occlusion query. So we had to come up with this kind of a mechanism. And then we slowly came to the realization that, okay, this would actually solve a more complex problem, which is if the scene doesn't change much, if the view doesn't change much, things are almost sorted, so how do we sort it? And then we came back and said, okay, now if you can map this onto the linear arrays, how do we basically proceed from there? And we apply similar algorithms. So does that answer your question in some manner? Right, so the algorithm that we have talked about, I mean, at least I'm not aware of any prior literature talking about it. This is not the best way of implementing sorting if you are doing any random sequence, because it could be order n square minus n root n. The complex is. So this will work well if the number of sorted elements are small. So if you are doing something like collision detection, so you have a game scene, things are moving slowly, and most of the collisions are going to be similar. If you need to do a sort over there, you already start with a sorted sequence because you're sorting the previous frame. So in those kind of scenarios, this kind of an algorithm will work much better than a byte-only sort-based algorithm. But if you don't know anything about your input data, you'd be better off starting with something like byte-only sort.
So by the way, just one quick comment. In the process of condensing this course from one semester to a week, we took away the explanation of the prefix scan algorithm. For those of you who wish to have a little bit more background in prefix scan, go to the UC498 website and look at our explanation of prefix scan. A lot of things that will make you more.
Okay. Thanks, Sunday. So next I'm going to talk about how you could implement general sorting on GPU. So if you have general data sets and you do not have any idea about the extent of sorted order, how do we achieve high performance while doing the sorting on? So in order to do that, we have designed a sorting algorithm with deterministic memory accesses. Our goal was to achieve high memory bandwidth, and therefore determinism actually makes a big difference in terms of how much memory bandwidth you can achieve on time. And we wanted to use minimum and maximum operations. There was a reason why we started with this. It's also mainly because in some way the graphics pipeline forced us to go back and rethink how you would map these primitives onto the graphics pipeline. And since we were forced to think about it, we actually were able to basically come up with these algorithms. So the byte-only sort algorithm requires just minimum and maximum operations. It has low branching overhead since it's such a predication operations, and it has no data dependencies. So you could utilize the high parallelism which is available on the GPUs. So we represented our data as 2D arrays, and we proceeded using a multi-stage algorithm. Each stage involves multiple steps, and within each step, we compare one array element exactly with one other element at a fixed distance. And then we perform a conditional assignment, which is either a minimum operation or a maximum operation at that element location. So again, I'm going to show a graphical illustration of how this is implemented in a periodic balance sorting network. And the byte-only sort is very similar to this. So here we have 8 elements. And as I mentioned earlier, we design a network where each element is compared with an element at a fixed distance. So over here, what we do is we perform a minimum operation at the tail of an arrow and a maximum operation at the head of the arrow. And this conceptually splits the array into two portions. Portions where minimum operations are performed and portions where maximum operations are performed. And the elements at the arrow tails are compared against the elements at the arrow heads. And how do we do this efficiently? So in GPUs, there was this notion called texture mapping. So earlier we used to represent all of our data inside textures. And this is actually done pretty much free of cost if you basically map your algorithm onto the texture mapping hardware. And then each element is compared against the corresponding element. So for doing the minimum operations, we have to do the blending operation, which is actually a less than operation and a greater than operation. And each element is then written back into the framework. So note that each operation is being performed independently of the remaining elements. So all of these will be done in parallel. So you can achieve a huge amount of parallelism and high speedups when you map this algorithm efficiently onto the GPUs. After this, this frame buffer is sent as the input to the next stage. Again, we input a network out over there. We conceptually decompose the arrays, perform all this mapping, do the blending operations, and write the result back into the frame buffer. And this is again sent as the input to the next stage. And we do the same set of operations over here, perform the blending operations, and then write the input back into the frame buffer. So for the entire array to be sorted, you need to repeat these three stages another 2 more times, and then the array becomes sorted. This also illustrates how painful it is to actually implement the algorithms inside the graphics pipeline. But it allows you to be more structured and to go back and rethink about how you would actually map the algorithms onto the architecture. So GPUs are optimized for 2D representations as opposed to 1D representations. So we had to map these 1D arrays as 2D arrays. And once we do this mapping, we can notice that the minimum and maximum regions map to row-aligned or column-aligned quads. So here's an example of how this mapping worked earlier. So here we have an array, and I have color-coded the regions where minimum operations are performed in orange and maximum operations as green. And when you map this 1D to a 2D array, these regions align with each other. So you need to perform minimum operations on a column-aligned quad over here. You are performing the same set of operations on a large number of elements. So you are essentially reducing the number of instructions which are being performed per element. And this makes it more efficient. So here's how sorting is mapped on a GPU in the traditional GPU sense in the years 2005 and 2006. So we had to send a bunch of quads to the GPU. These quads basically get rasterized and using the vertex processing engines over here. Then the mapping is performed inside texturing engines over here. And in parallel, you were able to perform comparison operations between the blending units on the GPU. And the writes are being performed sequentially into the memory frame buffer. So you can notice that we are able to utilize almost each stage of the graphics pipeline quite efficiently. And since we were able to do that, we were able to achieve significant performance improvements as compared to prior algorithms. So here is some performance numbers of how we compared against the prior sorting algorithm. So in 2003, Pulsar et al. Have done the first byte sort algorithm. This was just a proof of concept implementation. It achieved pretty good speedups. And then it was improved by Kiffer et al. In 2005. We later improved it by using a periodic balance sorting network. And then in 2006, we were able to achieve nearly 6x performance improvement over prior algorithms. Now, how do you implement the sorting on recent GPU APIs? So one of the main advantages that you would basically see out over here is that there is a shared memory now. So you could perform these local sorting operations inside the shared memory. Now, once you look at how the algorithm is actually mapped from 1D to 2D, you can actually notice that the byte sorting can now be implemented in n log n memory accesses as opposed to n log square memory accesses. So you pretty much get a factor of log n performance improvement in terms of memory efficiency. And the memory access patterns are very similar to effective butterfly networks. So I'm going to just show some of the performance numbers that we had on FFTs on GPUs. And this is a recent paper that we wrote to supercomputing, and which will appear in 2008, November 2008. So here we show our numbers on GTX 280 using the optimized shared memory accesses and everything. And you can notice that by actually optimizing the algorithm, you can get nearly 10 to 30x performance improvement over CPU-based algorithms. Also notice that by optimizing the implementation, we were actually able to get around 48x performance improvement than CUFFT on the same GPU. The GPU achieves nearly a quarter of a teraflop performance. And the interesting thing to note is that even on a half performance GPU, which is like G92, we were able to achieve almost 2x performance improvement compared to some of the optimized libraries available out over there. And this performance is going to improve in the coming few generations based on the hardware improvements coming with the NVIDIA. So I'm going to switch gears now and talk about external memory sorting. So far I have talked about how sorting algorithms can be implemented when the data is in the main memory. It is available inside Microsoft. Okay. If you need it, yeah, we can basically get it. Okay. So I'm going to talk now on about how sorting can be implemented on large terabyte scale databases. And as I mentioned earlier, these databases do not fit inside the main memories either on CPUs or on GPUs. So it usually proceeds in two phases. The first phase partitions the input file into large data chunks and writes the sorted chunks known as runs. And the second phase merges these runs to generate the sorted files. So the second phase is nothing but a merge sort which is happening on these runs. Performance of external memory sorting is mainly governed by the IO performance. And this is a big issue. So in the 90s, Betty Salzberg, Jingray, and a couple of colleagues have done an analysis on how the IO performance varies based on the memory size and the file size. So I'm just going to talk briefly about what their analysis means over here. So given a main memory size M and the file size N, if the IO read size per run is T in phase 2, that is if you're reading T bytes in phase 2 from each file, the external sorting algorithm achieves efficient IO performance if the run size R in phase 1 is given by square root of T times N. And how do you get this relationship? I'm not going to go into the details of that. Our paper in Sigma 2006 talks about some of these issues. But at a high level, if the file size is nearly 100 gigabytes, and if you are reading nearly 2 megabytes per run in the phase 2 to achieve good IO performance, then the run size that you need to have in phase 1 needs to be approximately 230 megabytes. And this amount of data doesn't fit inside the CPU cache. So large data sorting can be inefficient on CPUs, mainly because the run sizes need to be so large that they don't fit inside the cache. So you are pretty much limited by the memory latency. So this leads us to this dilemma over here that external memory sorting on CPUs can have low performance due to high memory latency because the run sizes are quite large, or you have low IO performance. That is, you can have small runs which fit inside the CPU caches, but that would mean that you have a large number of files and you can only read a small amount from each file. So the IO performance in phase 2 will suffer if you have small run sizes. So the algorithm that we have presented in Sigma 2006 sorts large data arrays on GPUs and performs the IO operations in parallel on the CPU. So we are using the GPU as a coprocessor to perform the sorting operations which are quite expensive on CPUs. So here's an architecture diagram of what we have done in that system. So we have a reader thread which reads the data asynchronously from the disks in parallel. There is a key pointer thread which generates the keys and the pointers and sends the data from the CPU, main memory, to the GPU. And on the GPU, we were utilizing the high memory bandwidth and performing the sorting of these key pointer routines in parallel. And the data is then sent back to the CPU, and then a reorder operation is performed on the entire data, and the data is then written to the disk in parallel. So this is a 5-phase pipeline where we were utilizing almost all aspects of the entire piece to achieve high performance. So we're using the disks, the memory on the system, the CPUs for generating key pointers and all the resource management, the GPUs for performing the sorting, and so on. So let me talk about how the I/O performance varied now when we use the system. So according to Betty Salzberg's analysis, if you have a 60 gigabyte database, we need to perform sorting of 100 megabyte runs to achieve good I/O performance. So this chart over here just shows the peak I/O if nothing is running on the PC. So if you're just performing I/O operations using a 2x2 RAID configuration on SATA disks, we got nearly 125 gigabytes per second. With 3x3, you get close to 175, and 4x4, you get close to 225 megabytes per second. We then used one of the optimized sorting routines on CPUs. In fact, it was the terabyte sorting winner on the CPUs at that point of time, called the NSORT routine. And since a single CPU does not perform this well enough, so basically we said, okay, let's use a 25 megabyte run size instead of using a 100 megabyte run size, and see how much performance we get. So we are doing essentially less amount of work than what we should, according to the analysis. But we are still getting only 75% I/O efficiency. So this is still not sufficient enough in the phase 1. The performance in phase 2 is going to be significantly worse, mainly because we are having a smaller run size. We then used dual 3.6 gigahertz Xeons. Again, we use the same run size, 25 MB. We put more cores. We are still doing less amount of work than what we should, and the I/O performance improved. So we were getting no difference in the I/O performance when we have a 2x2 configuration, and when we go for a 4x4 configuration, it's approximately 85% of the peak I/O that we were seeing. Then we use a 7800 GT GPU, and we use the ideal run size, 100 megabytes. And this is the ideal amount of work that we needed to have. And notice that the I/O performance over here is, and the performance is actually being done on a Pentium 4 CPU. It's not being done on the dual Xeons. So since we have ideal work, we are 92% I/O efficient, and we are using just a much more slower CPU. So what this shows is that the performance bottleneck is probably not in the I/O, but it's in the way the memory architecture is designed. So this graph over here shows the amount of task parallelism which is available at that point of time. The three GPUs that we have were 6800, 6800 Ultra, and 7800 GT GPU. And notice that the performance actually is not limited by the sorting performance. So the sorting performance is basically shown over here. And majority of the time is actually spent by I/O and the reordering stages. So what this means is that there is actually much more potential in terms of improving the sorting performance. We were getting almost close to peak I/O performances, but still the performance is actually not limited by the GPUs. It is actually limited by the I/O and the main memory. So if the main memory performance increases, the performance actually can be significantly better. So this chart over here highlights the performance of our algorithm as the data size increases. So this graph is interesting mainly because if you see the CPU sorting routine, it starts becoming slightly better than the GPU routine, somewhere around 53 gigabytes. And then as the data size increases, it starts becoming slower and slower. And this is mainly because as the data size becomes larger, you need to sort larger runs. And this is something which the CPUs are actually not good at doing, mainly because they are memory limited. And on the GPU, you can see that it scales well. So this is actually a potentially scalable solution than using a much more expensive dual Xeon processor solution. So performance per dollar is an important consideration because this makes a big difference in the database community. And over here we show the performance of our system as compared to dual 3.6 gigahertz Xeon. And we can see that the performance at that point of time, a 7800 GT GPU, which costed $250, was nearly 1.8x faster than the current the terabyte slot. Yes, correct?
So this is the P7, essentially.
Yes.
The old, smaller amount of DRAM on board.
Yes.
Smaller, lower end was CPU with 84.
That is true.
So I wasn't going to interrupt you. I actually thought maybe you would tell the secret, but at your convenience time, you can extrapolate, try to predict what this is going to look like with the bigger amount of
Right.
and the better interconnector.
So if I were to redesign the algorithm and the system, the entire sorting performance would at least increase by a factor of 10x right now, just because you have shared memory and you can do the algorithm in log n as opposed to in log square. I would also move the reorder stages onto the GPU because now we are not so memory limited. Also, the memory performance of the GPU has increased by 4x. So it doesn't make sense to do it on the CPUs anymore. You would actually send the entire data onto the GPU, perform all the sorting over there, and read it back and just do asynchronous IOs back to the disk. Yes, it was this card had 256 MB video memory, and we were using close to 20 MB because we were just using keys and pointers at the point of time. You could actually have a fairly big run. The runs that we're talking about is only 100 megabytes at this point of time, and you could have close to like 400 or 500 megabyte runs and still be able to get pretty high performances. In fact, one of the things that I need to mention on this benchmark is that for this benchmark requires you to sort 10 byte keys and 100 byte records. It's not small keys and small records. And that was the main motivation for actually having this is to not look at things which are small, but to look at large scale things and things which are commonly used in the database community. Any more questions? So there are several advantages of having this kind of coprocessor-based architecture. First of all, we were able to exploit the high memory bandwidth on the GPUs. And what this provides us is a higher memory performance than the CPU-based algorithms. Because we are memory limited, we are able to offload the memory computations out onto the GPUs. So we are getting the performance of both the CPUs as well as the GPUs. We are achieving higher performance because we are able to sort larger runs. In fact, GPUs are designed to work well on large datasets. So this actually is a pretty good fit in terms of using the capabilities of the GPUs. We are able to offload the work from the CPU. So see, as I noticed in one of the graphs that I've shown earlier, by using a dual Xeons, we are actually able to improve the I/O performance slightly. And this is mainly because the CPUs are starved at that point of time to perform the sorting operation. So by offloading the work from the CPUs, we are able to actually free up some of the cycles for the CPUs to do resource management operations. And based on the last chart that I've shown, it is actually a scalable solution for large databases since we are able to sort larger runs. So it works well on larger, as the size of the database increases. This is a better solution than the traditional solutions which are available. And last but not least, it's achieved the best performance to price solution for terabyte sorting in the year 2006. So, in conclusion, benchmarking is an important aspect for both the hardware vendors and the software vendors. Hopefully, I have convinced you guys that sorting is an important workload that we need to pay attention to. Another thing that I've talked about in this talk is about designing better algorithms on GPUs. We did not try to remap the serial algorithms and try to achieve a higher performance on GPUs. That may not be the right strategy. But we think about how we would map these algorithms onto these architectures. And designed by using scalable primitives. Example, use scans, which are quite well known in the high performance computing community, and they are used in a large number of operations. So use scalable primitives, libraries, for example, MapReduce is a good example, and exploit them for adaptive, general, and external memory sorting algorithms. Exploit the memory models. If you want to get good performance and scalable performance, you would want to use a shared memory which is available on the GPUs. I've shown that FFT algorithms currently can achieve nearly 4 teraflop on a single GPU. And this kind of a thing is applicable to many scientific computing algorithms. It's not just limited to sorting or FFTs, but it could be used for a wide range of computations. And last but not least, I've talked about a novel external memory sorting algorithm, the scalable solution. It achieves high performance on CPUs, and it achieves the best performance price solution in the FF216. In terms of the GPU roadmap, the GPUs are becoming more general purpose. There are lesser and lesser limitations in each generation of these standards. There are fewer limitations in the Microsoft DirectX 11 API. There is a consistent IEEE floating point support, and there is optional double support. This is integrated instruction support. There are more programmable stages. And if you exploit all of these capabilities, there is significant advancement in terms of performance. And you will also achieve portability as well as scalable performance. GPUs are being increasingly adapted in commercial applications. For example, they are widely used in image and media processing, codecs, signal processing algorithms, finance solutions, etc. Here's a call to action slide. So pay attention to the problem of data parallelism. Do not neglect it. Task parallelism is not the only way of achieving scalable performance. Don't put all your eggs in the multi-core basket. There are other kinds of parallel algorithms and which could be used. For example, the sorting system is a good example of how you can achieve better performance using a more balanced system. And if you want teraflops per second, and if that's the kind of applications you need, go use the architectures which use them. And if you want memory bandwidth, go use the architectures which has high memory bandwidth. And last but not least, the CPU to GPU performance gap is widening, and there will be a bunch of workloads which work better on GPU. So it's important that we pay attention to that. I'd like to acknowledge my collaborators, Jim Gray from Microsoft Research, a number of folks from UNC, Microsoft, supporters for the research that I've done. Most of this research has been done at UNC Chapel Hill before I was at Microsoft. Fred Brooks was the strong supporter for this research. Fred Mendy at Microsoft is also a big supporter for the research. Take any questions or comments?
Yeah, what's on a platform of Microsoft? The name of the accelerator.
Yes.
Since starting the year one. What went wrong? Why is it better? Why is accelerator?
If you want to do programming in C#, probably you would still use accelerator. If you want to use C# as your programming environment, you would still want to use accelerator. So
if I had a program in two lines, one in C, two lines C, and one in C# in accelerator, is it just from the language?
the goals of the environments are fairly different. So it's kind of difficult to answer, what's better and what's not, right? So because ease of programming, managed environments do a lot of things for you. And there is more work going on in that area inside Microsoft.
Yeah, so it's something to expect to continue and get better.
That's the hope, yes.
So you have Emacs program with you. What was your background in terms of parallel development? What sort of, in other words, basically thinking more in terms of use of algorithms for sort of what happens in theoretical models and theorem models and sort of more traditional distributed memory sort of way of looking at parallel programming. So what background you have in parallel programming, what sort of where do you draw those equations from?
Right. My background has been actually in graphics. My PhD is in graphics. Before I started working on the GPU stuff, I was working on large data visualization. At that point of time, NVIDIA had this first set of features in GeForce 3 and 4 architectures called register combiners. And there was a bunch of work going on at UNC in terms of doing fluid simulations, mainly by Mark Harris, who's now at NVIDIA. And that started a bunch of research inside UNC. And we started looking at what other algorithms can actually map well onto this kind of an architecture, and why is this architecture actually better in doing these problems. So our background has not been in parallel computing, but having some understanding about what's done in the previous literature is always helpful in knowing how you would want to design your algorithm onto different architectures. So having a curriculum in parallel computing in the undergrad would help a lot of programmers work on these new architectures.
In the working algorithm that you application, it had a virtual key. I was wondering how you achieve that since I believe the description on using a function for GPU.
So which portion? The phase 1 basically is implemented purely using bytecode sort. The phase 2 did not turn out to be a big issue because we were able to sort large runs. We just had to do a merge sort, and merge sort is basically not compute intensive. That's true. That's true.
So I have a question. So sorting always is one of those things that I like because it's not a stringy application per se. So a lot of applications you can kind of string data to system lines and that. But sorting is something that you maybe go back to your other piece of data, so it's not a stringy application.
Right.
But sorting is also something that you can somewhat easily do a divided function as we illustrated here. So in my mind, if you have a stringing application, it could be very nice to use. And if you have a non-stringing application, as we demonstrated here, if you can divide and conquer, you can have a good usage of GPU. Do you see a lot of things that don't fall in one of these categories and that still need to be figured out?
That's a good question. It's actually a very tough question to answer. Well, I don't have an answer for you. But there are a bunch of whole class of problems which probably wouldn't map well onto the GPUs at this point of time. But hardware is evolving, and you could implement some of these things more efficiently. I mean, something could not be done at this point of time does not mean that you cannot do it. It's just that you maybe have overlooked some aspect, or you may need to redesign the algorithm. The adaptive sorting algorithm that I talked about is an interesting example of the same kind of a thing. When people come and say you cannot sort, almost sorted sequences, you may want to go back and think about, okay, I have a bunch of tricks in my bag. Can I use any of those to redesign the thing? So it in some way forces us to basically go back and rethink our assumptions about the algorithms. So it's an opportunity for innovation in some way.
So how would you implement that on GPU? Just anything that has pointers,
So quicksort is a very good example too, in some way, and that could be done alternatively using Python sort or other kinds of sorting algorithms. It's not a sufficient condition.
Also, in fact, what you said is an interesting response that I've seen other people do. That is, you know what, I have a question is sorting. You can use the funny sort, you can use quicksort, you can use other efficient sort, right? And you know what, the quicksort will actually give you this kind of meta behavior that you can use for the funny sort to figure out on the spot.
Right.
So maybe you need to find, or maybe you have to figure out the right approach to it. Any other? You know, this is a very rare opportunity. You know, this is a person who has been the thing, reading the thing for years, and you know, it's not
the case that we can find someone like him to ask questions. Okay, these people, this is your opportunity. So make the most out of it.
Let me just mention also one other thing, just to embarrass Naga a little bit more. That graph he showed, this code for FFT kicks the snot out of the code that people wrote who do that for a living. I mean, that's all they do. So this is really a tremendous achievement. So if you guys have any deep questions about, could I implement this or whatever, he knows more about it than almost anybody.
Oh, now you are putting me on spot.
Okay, so there's another question.
And what I'm doing with my data work right now, there's game application, data modeling for you're not going to trust. Game application basically, you have a fixed size amount of memory and kind of multiple data and training application as well as on the CPU. The method for sorting the data by being alive and dead, and then using the right-hand side basically for dead, going to replicate. And the first sorting method that we did, where you have fewer sort of things, how would you say, how difficult is that to implement? Is it a intensive sort of process, or?
It is. I think, as I said, hardware will improve over a period of time. That portion that you're talking about would be done better if you have a programmable command processor. Wouldn't that be nice? So maybe that's a suggestion to David. And maybe you could.
You might be moving this point, but if you could repeat or summarize people's questions for the people that are listening to the stream video.
Oh, I completely forgot about that. Yeah. So the question was, so the application that name Ryan, the application that Ryan has requires dynamic memory allocation, and he asks about how difficult it is to implement the sorting algorithm, the rapid sorting algorithm that we have done, mainly because it requires some amount of communication with the CPU as well. And the thing that I'm trying to do is that hardware will become more and more accessible for doing those kind of operations. If you have a programmable command processor which is not too expensive to implement, and if the vendors implement it, that kind of a problem can be done much more easily. So it's something that the vendors have to consider whether there's something in the market for them to actually use those kind of solutions.
So any other questions? If not, Nega is going to be here a little bit longer until the virtual school feedback session. So again, this is a rare opportunity for you to ask some questions in person. But at this point, thank you, Nega.
Thank you.